Hello everyone and welcome back. Today I'd like to introduce you to two subtopics, and whether they're mentioned by name or not, they have a habit of rearing their ugly head every now and then simply because they're very closely connected to forces and energy. We're going to start with the term mechanical advantage. Now, by definition, mechanical advantage is a ratio that gives a force advantage of a tool. In short, every tool you use, pliers, screwdriver, hammer, a ramp, gives you a force advantage in one form or another, and that force advantage has an official name called the mechanical advantage of the tool. Now, here is what the traditional equation looks like. Mechanical advantage equals force out over force in. But since these two things sound very similar, people often forget what they are. So let's take a moment and actually define them. To start out, the force in is the force you exert with the tool, and force out is the force you would need to exert without the tool. To give you an example of what I'm talking about, let's pull up a pulley system. So here I have my guy pulling on the rope. Let's say the rope is pulling on him with 100 newtons. Therefore, he is also pulling the rope with 100 newtons, because nothing here is moving. That means this rope is pulling on this pulley with 100, it is pulling on this pulley with 100, this one with 100, and this one with 100. Now, let's concentrate on this pulley over here. That means if I do a force diagram of this pulley, that means I have 200 newtons upward, and if nothing is moving right now, 200 newtons downward. Now let's pretend this person is using this contraption to lift this item. That means this person is exerting 100 newtons on the rope, and the tool, which is the pulley system, is exerting 200 newtons on the box. So if I took a look at my mechanical advantage formula, force in is the force exerted with the tool. So with the tool, this person exerting 100 newtons. However, if this person did not have the tool, they would have to exert 200 newtons to lift the box. So the force out is 200 newtons. Newtons would cancel, and therefore the mechanical advantage of this would be 2. In other words, he's getting twice the amount of force out that he is putting in. So while we're here, a quick note. Mechanical advantage should always be above 1, otherwise it's not really an advantage. So mechanical advantage is about forces. How much force you put in and how much force you get out of the tool. Notice it's a pure ratio. If he tripled his force, this value would triple as well. Okay then, what is efficiency? Efficiency is the ratio of energy going to where you want it to over how much total energy was transferred. Now there's a reason why I'm doing these two together. The reason is because the equations look very similar, and I'm doing them back to back to try to give you ideas on how you can not confuse them, and make sure you can take notes on how to separate the numerator and the denominator, because again, efficiency is written in a way that's a little confusing. Efficiency is work out over work in. All right, so what the heck is work out and what the heck is work in? Well, work in is the total energy transferred. This means, let's say you climb a set of stairs and you burn 100 joules of energy from your lunch. Your goal is to gain gravitational potential energy. However, as you climb the stairs, your body will warm up as well, which is internal energy. So not all the energy you're burning is going to where you want it to go. Work out is the energy you want. So in my example here, if you burn 100 joules of energy to climb a set of stairs, if 30 joules of that energy went into gravitational potential energy and 70 joules of that energy went into internal thermal energy, then your body would be 30% efficient. And believe it or not, for the human body, that is pretty good. So let me give you an actual example here. Let's say I have this go-kart. It starts on rest, it accelerates down a track that is 100 meters long. At the end of the track, it reaches 50 meters a second. There's a frictional force of the car 180 newtons the entire time, and the mass of the go-kart is 200 kilograms. Now looking at my bar graph, there's no initial. I have work equals kinetic final plus internal. So the work done is the total energy transferred. The driver wants kinetic energy, but can't help but have some of the energy transferred to internal energy due to air friction. So our system here is the go-kart in the air. If I drop this, I get work equals 1F mvf squared plus force friction delta D. Notice I don't need time at all for this, and that's because this problem is not dealing with power like we did last time. 1F 200 kilograms times 50 meters a second squared plus 180 newtons times 100 meters gives me 250,000 joules plus 18,000 joules, which gives me a total transfer of 268,000 joules. Now, efficiency, work in, is the total energy transferred. That is this. The energy transferred from the chemical energy in the gasoline, which is not considered to be in the system, is 268,000 joules. The energy the driver wants is kinetic energy, and that is this, 250,000 joules. Again, units cancel. This would give me 0.93, or as it's usually put, 93% efficiency. So 93% of the energy that was transferred goes to where you want it to go. So 93% of the energy goes into kinetic energy, which is where the driver wants it to go. The other 7% went to internal, which is useless to the driver. In truth, there'd be internal frictional forces in the vehicle, which would lower this percentage, but this makes good for a simple example. The work in is the total energy transferred, which is the entire work done. Work out is the energy you want, which in this case was kinetic energy, and I purposely kept the air in the system so I can keep internal on my bar graph and separate it from work. Now, a little side note, efficiency has a very close relationship with thermodynamics as well, especially the second law, which you'll be dealing with in AP2. And what I'm about to put up is going to come back again much later. Only a frictionless machine can be 100% efficient. This is basically one of the reasons why you can't have a perpetual motion machine. The US Patent Office gets a bunch of them every year and simply throws them in the trash. Alright, let's do a problem that actually takes both of these into account. And for that, I'm going to use a simple ramp. The ramp is 8 meters long, the angle to the ground is 30 degrees, the mass of the yellow box here is 50 kilograms, and the coefficient of friction on the ramp is 0.23. Now, we're going to take a look at this two ways. One, pushing the box up the ramp at a constant velocity, and two, lifting the box straight up into the air at a constant velocity. And I'm saying the words constant velocity to show that we are not going to deal with kinetic energy here. The whole point of a ramp is to lift something into the air and put it on a truck or something. So we are dealing with an increase in gravitational potential energy. In other words, you could also think of it as box starts at rest on the ground, box ends up at rest on the truck. So in my initial state and final state, kinetic energy is 0. That also means my system is the box and the earth. Now, I'm going to start with the lift. And I will put my two new equations down here for reference. All right, to start, I'm going to make these some variables. So I'm going to say this length is L. That means if this is 30 degrees, this is 8 meters, this is L sine theta. So for the lift, we're going to find the work done, which means we need force parallel. Well, force earth is mg, therefore force person on box, which is my force parallel, is also mg. Work, therefore, is force person on box times change in height would be mg times change in height, which is the formula for change of gravitational potential energy. Expanding this, I get mg L sine theta, which is 50 kilograms times 9.8 newtons per meter, times 8 meters, which is L, and 0.5, which is sine 30 degrees. Next line, I'm going to separate this out. The force is 490 newtons, and the height is 4 meters, which would be 1960 joules of work if you lifted it straight up into the air. All right, let's start the force diagram on the ramp. I have force earth, which is mg. This is force parallel. This is force perpendicular. Force parallel is mg sine theta. Force perpendicular is mg cosine theta. Force normal is mg cosine theta. And I'm going to pause here for a minute. The force someone would need to exert in order to push this up the ramp would be this way. This would be force person on box, which would be my force parallel. I want to do a quick look to see what the work would be without friction. That'd be force person on box, which is my parallel force, times my distance, which is L. Now, force earth is split up, so it's gone. Force perpendicular cancels out with force normal, so they're gone. Which means in order to push this box up the ramp at a constant velocity, force person on box would have to match force parallel. Which means this equation expands to mg sine theta times L. Now, if you notice, this and this are the exact same equation. So if this ramp is frictionless, I'm not even going to bother doing the math. If the ramp is frictionless, the work done will be 1960 joules. So if the work is the same, why bother using the ramp? Well, we're going to answer that question, but we're going to actually ask a more difficult question. But the first thing I'm going to do is add friction to the ramp. Now, that means I have a frictional force going this way. Force friction is mu times force normal, which is mu mg cosine theta. So work with friction on the ramp would still be force person on box times L, except force person on box would now be longer because the person pushing now has to account for friction and for force parallel. That'd be mg sine theta plus mu mg cosine theta times L. 50 kilograms times 9.8 newtons per kilogram times 0.5 plus 0.23 times 50 kilograms times 9.8 newtons per kilogram times 0.866, which is cosine theta, times the 8 meters, because that's the length up the ramp. Dropping that, I get 245 newtons, which is force parallel, plus 97.6 newtons, which is force friction, times 8 meters, gives me 342.6 newtons, which is force person on box, times 8 meters, gives me 27.41 joules. So this is the amount of work done with the ramp, with friction. So if you lift the box straight up into the air, you are doing less work than if you use the ramp. Now, the big question is, why would you then use the ramp? Even with this friction, the ramp is still an advantage. And the question is why? First, since we have all the energies up, let's take a look at the efficiency. The efficiency is work out over work in. Work in is the total amount of work you do, which is what we have here with friction, 2741 joules. This is the total amount of energy you transferred. Work out is where you wanted that energy to go. You wanted gravitational potential energy, which is what you have with the direct lift. That is 1960 joules. These cancel, and I get efficiency of 0.715 or 71.5%. Okay, now to answer our question. Why would you use the ramp? Well, looking at the work we did here, this value, the 490 newtons, represents how much force you would need to lift this box straight up into the air. However, this value represents force person on box when you're pushing the box up the ramp. So the 490 newtons, how much force you need to lift it straight upward. The 342.6 newtons is how much force you would need to push it up the ramp. Even with friction, this is a lower value. So even though you're spending more energy pushing up the ramp, you're using less force. You're using less force over a greater distance. To lift it, it's 4 meters. But to push it up the ramp, it's 8 meters, which is a bit of a downside, but it's a downside people are happy to deal with because they are applying less force and are less likely to hurt themselves by moving this box to a higher surface. So let's take a look at the mechanical advantage. Mechanical advantage is force out over force in. Force in is the force you use with the tool, 342.6 newtons. Force out is the force without the tool, 490 newtons. These cancel, and I get a mechanical advantage of 1.43 times. Side note, this is sometimes called a force advantage. So if the ramp is frictionless, you would do the same amount of work. If the ramp is not frictionless, you would do more work. However, even with the friction, you need to exert less force to push the box up the ramp. As a side note, if the ramp is frictionless and you want to find the mechanical advantage, you would use this value because this value is equal to force parallel. And with no friction, this is the value you would use to push the box up the ramp. And if you notice, since it would be an even smaller denominator than what we used, you'll get a larger mechanical advantage, which would make sense because the lower the friction is, the less force you need to work against.
All right. There's one more thing I would like to show you while I'm here, and that is that both mechanical advantage and efficiency can both be easily reduced typically before you put in any numbers. And I'm going to show that to you with the ramp. First, we have mechanical advantage, force out over force in. Well, force out is equivalent to force earth on object. Force in is equivalent to force parallel plus force friction on object pushing it up the ramp. Breaking this down gives us mg over mg sine theta plus mu mg cosine theta. Now, take a look at what cancels. We cancel m, we cancel g, which means what we have left is 1 over sine theta plus mu cosine theta. And to note, without friction, this mu cosine theta wouldn't be here, and you would just have 1 over sine theta. Now for efficiency. Well, for efficiency, work out would be the work done without the tool. In other words, force earth on object times the height. Work in would be force parallel plus force friction times the length. That would give us mg L sine theta, where L sine theta is the height, over mg sine theta plus mu mg cosine theta times L. Now what cancels here? Well, once again, M and G both cancel, and L cancels, and you end up with this. Sine theta over sine theta plus mu cosine theta. So if you're dealing with mechanical advantage or efficiency, it is highly recommended that you set everything up in variable form first and see what cancels. It is actually usually quite typical, in fact, that you are not given the mass for these problems, and that's actually a very big hint that somewhere along the way, mass will cancel. All right, I hope this helped you out with these two topics. Have a good day. This is Mr. M, signing off.